Good morning, class, and welcome to this lesson on Electrostatics 11 parallel plate capacitors. Today, we will be able to describe some basic characteristics of capacitors. So far in electrostatics, we have talked about point charges and voltages and electric fields and forces and things like that. And really, a lot of that is very theoretical. A capacitor is kind of nice because a capacitor is a very practical application of charge and electric fields and everything else. So a parallel plate capacitor is pretty much what it sounds like. We have two parallel conducting plates that are separated. Okay, and with these two conducting plates, these plates store charge. These store charge. And that's where we get the term capacitor. It has a capacity for charge. It stores charge. So just be careful. It does not create charge. It does not create charge. It just stores it. And I'll give you an analogy for this in a second. So what happens here, we have these two parallel plates. And I'll draw a simple diagram down here. We have two parallel plates. Okay, these parallel plates are going to be connected to a battery, some sort of battery. Okay, this is a symbol for a battery. This is a symbol for a capacitor. And this is going to be the positive end of the battery, and this is a negative end of the battery. And what a battery does when it's connected to a capacitor, a battery removes charges, it removes electrons from one side, and it moves them over to the other side. So what happens is we have a positive charge plate on one side and a negative charge plate on the other side, as you can see from this picture right here. Okay? And so, once again, the battery moves the charge. The battery moves the charge. Okay? It helps create the charge. Okay? A battery can create it. A capacitor can store it. Okay? Different. So, what we now have are we have a positive plate and a negative plate. And because of that, we now have an electric field in between these two, going from positive to negative. And I'm going to go on to the next page. We have an electric field going from positive to negative. And because there is so much charge right here, because this is really a lot of charge, we have a lot of charge on this end and a lot of charge on this end, what we find here in the middle is that we have a uniform electric field. We discussed before that with an electric field will decrease with a point charge with a change in radius, okay? So the further away we get away from it, the more the electric field decreases. Well, in a capacitor, the electric field is constant all the way throughout. So we have a nice uniform electric field in the middle here. Okay? So that's kind of nice. What we also find is on the outside of the capacitor, so on this side over here, the electric field is equal to 0. And on this side is equal to 0. So there's only electric field inside the capacitor, only inside. Okay? Only inside the capacitor, the electric field. And that is because there's so many charges that even on the outside of the capacitor, if there's an electric field out here, it cancels out with the positive will cancel out the negative on this side, and then the negative will cancel out with the positive on this side. So really, we have a concentrated electric field right in the middle of these two plates. Okay, we've got these two parallel plates. Okay. So once again, let's kind of go back here for a second. We have a capacitor. A capacitor stores charge. It stores charge. It does not create charge. A battery moves charge. A battery is like the pump. Okay? Pretend you had a big container. Okay, you had a big container with the hose, and then you had a water pump connected to a lake. Okay? This analogy isn't perfect, but a battery is like the pump. A battery will move the water from the lake into the container. So the pump is like the battery, and then the container is like the capacitor. It can store charge. Okay? Now, because it can store charge, a very common application of this is a camera. Think of a camera. Okay, I'm gonna draw a very basic old camera here. Okay. Okay, think of a camera. Think about a camera you've had that takes a flash. Okay, there's a flash in the camera. Have you ever noticed that after you take a picture, it takes a little bit of time um, for you to take another picture with the flash? It has to like reset itself. Well, the reason is inside this camera there's a capacitor, and when you take a picture, basically all this charge is released. All this charge is released in order to power the light bulb. So it's a large amount of charge that is released very quickly to power something else. Okay? Because your battery couldn't power the light bulb. It couldn't take that much energy that quickly. So we have all this stored up on the plates. We have all this charge stored up, and then once we push that button, this charge is released and the flash goes. Well, so you take a picture, but it now is going to take a few seconds for the battery to charge the capacitor back up in order to get you ready for a flash again. That's why it takes a few seconds to take a picture again. So that's one very, very common example of how capacitors are important. Okay, it's one very common example of how capacitors are important because capacitors can store charge, and because they can store it, when you need it, they can also release it very quickly, much quicker than what a battery can producing it. Okay, and I'm just going to go over this one more time. I went over this in my last video, but when we have a uniform electric field, we can calculate the work done, and when we know that work is equal to force times distance, we know that force is equal to Q times E times D, and we can use this equation because E is in a uniform electric field. Okay, and if we divide both sides by Q, W over Q is equal to voltage, and so our voltage is equal to E times D. E times D. D being the distance in between the two plates. So we can calculate our voltage very quickly inside a capacitor because we have a uniform electric field and we know how far away the plates are. So this is a very simple way to understand how much voltage we can store inside a capacitor.